Hi class, we're on the next section, chapter 4.3, Logarithmic Functions. So logarithmic functions are the counterpart to our natural exponential function. So the way that they interact with each other is that they are inverses of each other. So a logarithm is the inverse of an exponential function. So if we have an exponential function where our base is b, then the inverse function of b to the x is log base b of x, right? So that's the way that we say this. So if this was a 5, we would say log base 5 of x, right? If our function is a logarithmic function, right, log base b of x, then the inverse of our function is b to the x, right? So they're inverses of each other. We saw in chapter 2 how inverses work. So if you're fuzzy on inverse functions, then I suggest you go back to chapter 2, I think it was 2.5 or something to that effect, to brush up on your inverse functions. Okay, now we saw that in the last section that our natural exponent e is a natural exponential function. So here we can say log base e of x, but since e is the natural exponent, we have a natural logarithm, right? So the inverse of the natural exponential function is natural log, right? So this is a French term here, logarithmique naturel. So that's why it's ln and not nl. So the log base e, we just rewrite it as ln. That's our natural log function. So same as before for these two, if our original function is the natural log function, then its inverse function is e to the x. Okay. If we do not see a base present, if it doesn't say, if there's no b here, if it's just log of x, then that means that our base is the standard base, which is our base 10. Okay. So the reason why the standard base is 10 is because we have 10 fingers, 10 toes, right? Our number system is based off of tens, right? 10, 20, 30, 40, 50. Everything counts by 10. So our standard base is a base 10. So if you see no value here, it's saying it's 10 to whatever power for the inverse function, right? It's a base of 10. So if y equals b to the x, okay, one way to remember that you have to go this is when it's log, this is what your base is, okay? But this x is your exponent here, okay? It's actually your output, okay? So when we have our function written in this standard form, y equals b to the x, the way I always think about it is we start at the base. So when we're writing in logs, the first thing that you're going to see is the base. So it'll say log and then your base. And we're going to move clockwise. The second thing that appears in the log form is y. So what's going on inside of here is our y. And then the last thing that you're going to see equation-wise is this x. Okay. So log b first of y, whatever this value is, equals x, 3. So you go in a clockwise fashion, starting at b, because that's the base, log base b, input goes y, and then x. So that's how I remember the order, is I just think about starting at b and going clockwise. Okay. So let's do an example. So if I have 12 squared equals 144, which is obviously a true fact, right? In logarithmic form, I'm going to have log base 12, okay? I'm going to go to the other side of the equal sign, right? It's written backwards than it is here. So I'm going to go to 144, right? The output becomes the input because it's an inverse function. And the input here becomes the output. So log 12 of 144 is 2. So for our next example, we have log. Notice that there is no base here, so that's base 10. So log of 1000 equals 3. In exponential form is a base of 10, exponent 3. What's on the inside is your output in the exponential form. So 10 to the third is 1000. For C, natural log of 1 equals 0, so we're using natural log, so our base is e. On this side of the equal sign, our output is what we would use here for an input. This input is our output, right? So again, remember it in terms of inverse functions of each other. It makes it a lot easier, right? So its input here is the output here, input, right? Out, in, out. Right? So those are just some quick examples of going back and forth between logarithmic form and exponential form. So if we talk about some of the properties of logarithms, this is not an extensive list. We're going to go over those in the next couple of sections. But the basic properties of logarithms is that if we have a log base b of 1, well, think about what that means in terms of exponents, right? It would be b to what will equal 1, right? So the only time you can get 1 out for an exponent is when you have 0 as the exponent. So in log form, log to any base of 1 is always going to equal 0. Okay. Here, the only way to have b raised to a power and get b out is if it's 1. So the log of log b of b is going to be 1. Log b of b to the x is going to be x. And here, if you have a base raised to a logarithm with its self as the base, it basically cancels everything out, and all you're left with is the interior value of the logarithm. So that will equal m. Okay. So this is a graph of our logarithm, basic base 10 log. So we saw this in chapter 2 when we went over the library of functions, and I think it was 2.2. But just to revisit that, this is what it is. Notice that log of 1 is 0, right? That's an important value because that's what happens when you plug in 1, right? Because of the way that exponential functions work. We cannot plug in any negative values, right? Let's go back up here, okay. For an exponential function, there's no way for me to plug in any value here to make this entire output value negative. That will never work. So since I can never get out a negative value, I cannot plug in to the inverse function of this a negative value, right? So my domain for log is only positive values, and I also cannot have 0 because, as we discussed before, I can never plug something into this function to make it an output of 0. And so since I can never get 0 out, I am not allowed to plug 0 in as an input. So my domain for log functions, any log, any base, is from 0 to infinity, 0 not being included. Okay. So I can get very, very, very close to the line x equals 0, right? But I can't actually plug 0 into here. But I can plug in very, very small values, 0.000001, right? But I can't plug in any 0, and I can't plug in anything negative. So let's do some examples. Let's say we want to solve log base 3 of 1 over 27 equals x. As it stands right now, we can't really solve it in the way that it is. So when we're dealing with logarithmic functions and with exponential functions, a lot of times we have to use their inverse counterpart, right? So I don't really know what it means to plug this into a calculator, or what this is very confusing, log base 3 of 1 over 127. So in order to solve for this, I have to put it into exponential form, right? So a lot of times for logarithms, we have to put it into exponential form in order to solve. And a lot of time when we have an exponential problem, we have to put it into logarithmic form in order to solve, and then possibly back into exponential form. So we want to be able to go back and forth between log and exponential forms so that we can solve these kinds of problems, right? So if I want to put this in exponential form, it'll be 3 to the x equals 1 over 27. Okay. Now it's a lot easier for me to try to solve this, okay? I know 27 is a power of 3, so let's rewrite this as a power of 3, right? So that's 1 over 3 to the cubed. And I want to try to put this side, the right-hand side, into a standard base b form. Well, I know that when my number is on the denominator with 1 in the numerator, I need to use a negative exponent, right? So I can rewrite this as 3 to the negative 3. And so if 3x is equal to 3 to negative 3, well, those exponents have to be equal to each other. So I get a value of x equals negative 3 for my answer. Okay. Now if I want to do the same thing, I want to solve natural log of x equals 5. I'm going to do the same thing. I'm going to put this into exponential form. I got to remember that my base is e. So I'll go e to the 5th equals x. And that's my answer, right? Remember, e is a number. I don't want to put this into its decimal form because that would be like saying, okay, what's pi squared? Well, pi squared is pi squared. I don't actually multiply it out and then write the decimal form. This is an exact value. E is not a variable, it's a number. The answer here is e to the 5. Okay. This one's a little different. Instead of giving me the base is a thing that's unknown. Okay. So my base is x. I'm going to raise that to the power of 2/3, and that has to equal 9. Well, this is pretty straightforward. If I want to solve this, I raise both sides to the reciprocal power. So I'm going to raise this to the 3/2. I'm going to raise this to the 3/2. Okay, so that'll cancel this. This is kind of okay as an answer. I'd like to simplify this if I can. So I know 9 is the same thing as 3 squared, which is nice because I have a fractional exponent with a denominator of 2. So if I can write this as something squared and get those to cancel, it'll be beneficial for me, right? So the 2's cancel and this turns into 3 cubed or 27, right? 27 is a much nicer answer than 9 to the 3/2 power. And that's how we deal with various logarithmic problems in this section.